class again here at 11:45, and we have lab in the afternoon. We're going to be playing with some more toys on Monday inside the lab, and those toys happen to be from the cabinet marked electronics. And of course, the reason why we're playing with electronics is I mentioned earlier that we're going to be building a prototype barcode scanner. We need a system. We'll be introducing this much more in depth as we go through the course. Everybody knows what a barcode is, and that's why we picked this technology. Everybody, there you go. That's it. You have the twin. Everybody knows what a barcode is, so the idea is that when we look to see why a barcode is used systems-wise and how it is read by the scanner and how the information is processed, we don't have to introduce something that's not familiar and then get into the idea of how it works. We want it to examine something that somebody already knows. Of course, there are other things that people already know, but a barcode seems to be it. We are going to be looking at the basic electronics necessary to build a prototype barcode scanner. We're then going to look at the basic software programming necessary to build a barcode scanner. Our prototype barcode scanner, obviously we're using 2016 tools. We're going to use modern electronics and modern computers. However, back in the late 1960s, I think it was 1967, when the first barcode was ever demonstrated. I believe the trivia is that the first ever barcode was on a pack of Wrigley's Spearmint gum, and it was invented and scanned in Ohio. The state of Ohio is where the company first decided this would be a good idea to put these markings on products. They did not have, obviously, our modern equipment for their prototype. But rather than go back and then do the historically pure version of a prototype, which would have been pretty large electronics, we're going to make a prototype barcode scanner using modern electronics because it's sort of a simple thing to do, and then we can figure out how that it works. We're not building a store checkout barcode scanner that you could take home and use. It's going to be a prototype, and it's going to be a, hey, here's all the wires that are exposed, and here's all the components for us to look at because we want to see how this system gets put together. So to help us with our journey of talking about a barcode scanner, we've been talking about this idea of looking at the parts of a system as boxes. And whenever we talk about a box, we could say that that is a system, and the system has a boundary. There are things that are inside the box. There are things that flow into and out of the box, and the box itself has this important environment, if I can spell it properly. And it's all of those things that we need to consider whenever we talk about a particular system. So input, output, the process inside the box, and then the environment. Those are sort of the big four things that we're worried about. And I mentioned earlier when we were talking about these individual parts of a much larger system, every little tiny part usually consists of items. Let's just say it's a material thing, like our balloon. We know that a balloon is a single thing if we were to draw a box and title it balloon, but we know for a fact, because we've studied science and we've learned this through high school, and there are other ways to test these facts, that a balloon is not something that just pops into existence. It consists of parts that are smaller than the balloon itself. We know for a fact that it consists of molecules. They're typically called polymers. In fact, they're specifically called rubber. That allows us to stretch. These are latex molecules. And if you study chemistry even more, they were on the third floor, we know that latex molecules are comprised of individual atoms. And we know, because we've studied and we've tested these things, that the atoms themselves are all little systems. So when we talk about an atom, we can talk about the nucleus of the atom. We can talk about the electrons surrounding the outer shells of the atom. We know about neutrons and protons. We've never stopped talking about systems, okay? It's all parts. Even if you go down to physics and talk about quantum physics, we know that protons themselves are comprised of three particles inside the protons, three quarks they're called. We keep on getting smaller and smaller. We keep on discovering that stuff, no matter how we name it, or no matter how we draw the box, is comprised of smaller systems. And then we can use these parts to make bigger systems. You can go up or you can go down. Whenever we talk about a system, and we usually talk about the highest level system, I'll use the word system, but when we talk about the parts of a system, okay, we usually use the word component. So the reason why we don't necessarily say part, we can say part, there's nothing wrong with part, and I would never mark anybody wrong for using the word part, but sometimes parts can be an isolated part. Usually when we say the word component, it has a meaning that it belongs to a much larger system. There's nothing wrong with being a parts store. You go to the parts store, maybe it's an automotive parts store, and then you would buy some spark plugs and some windshield washer and some paint and a light bulb. Those are all parts. They obviously all go together to different types of cars. But when you're buying an integrated thing, say, God forbid, you need to replace your transmission, you're going to buy all the parts together that make one transmission. You would call that the component of the transmission. Or if you want to rebuild a particular engine, you would buy the components of the engine, things that go through. So not to belabor it, but I'll use the word component when we're talking about a smaller piece, and together the components to make a larger system. The reason why we started talking about the balloon, because it holds things and it provides push, we said that's very similar in electronics to a battery. Okay? So this system of a balloon, if I can spell it right, we said it sort of holds or contains, and it also provides push or pressure. And we can draw a similar box for a battery. It also holds, if I can scribble on here, and it pushes. This guy takes in air and it pushes out air. This guy takes in electrons and it pushes out electrons. What I want to do today is I'd like to start talking specifically about the electron system, because we need to measure the electron system. We're going to be working with electronics and electronic components on Monday, and we're going to build our barcode scanner. We know that the balloon consists of air, and we know that the push usually means pressure in force per unit area. We studied that last semester. Down here, the push is going to be volts, V-O-L-T-S. We're going to refer to how many volts that is. Of course, because volts is a component, the word itself has a whole bunch of history behind it and a whole bunch of stories behind it, but we're just going to go ahead and use it. I'd like us to figure out how much is a volt, how big is a volt. So what I've done is I've brought along a machine that measures how many volts. If you brought along a pressure gauge or a pressure meter, that would measure how much pressure is inside your tire, say certain PSI, pounds per square inch, or pascals. This is the device that measures how much push or how much pressure, specifically how many volts of electrons are inside the battery. And we're going to be using, this guy's called a voltmeter, who would have thought, because it measures volts. This guy also measures resistance in units of ohms, so you could also call it an ohm meter. And if it was measuring current in units of amps, it would be called an amp meter. This guy can do multiple things, so when we do play with this on Monday, you'll notice it says multimeter, because depending on what mode you put it in, it can measure different things. So what I wanted to do was up on the big screen, if I can get this guy to work, let me turn on our display. Let me make the front dark here so you can see it. What I want to do is I want to put the multimeter on the screen here. Let's see, I can see it's got words. I can see he's this is this particular Sony display needs to warm up. It also, everybody already knows, it's also electronic, and the light that it's producing is produced through electronics. And there's a whole bunch of wires supplying it with a certain amount of volts. And yes, there's resistance and there are currents, and it turns out that all of the resistors inside that device, that system we call a digital display, are all working together to hopefully display this image as soon as it comes up. Adjusting and bringing in. So that's just a picture of this multimeter over here. Okay. So what I'm going to do is I'm going to put this multimeter on volts. You can sort of see that it's displaying a digital value. The units are in volts over here. And it turns out that this guy happens to have a red and a black probe to it. We mentioned before that a battery and volts, usually the electrons come out of the output, they swing around the wire, and then go back into the input. We saw before, if you don't mind me drawing this picture again, we said if this is a battery, one way to view it is that there's a sort of a division. There's lots of high pressure electrons over here where it's been pumped up, and there's not a lot of electrons over here. So rather than just spilling it out into the atmosphere, you guys familiar with electricity? What would happen if I was just spilling volts out into the atmosphere, just filling the room with electrons? What would that look like? What would it smell like? What would it sound like? Have you ever seen electrons just spilling out into the atmosphere?
Yeah.
What is it?
It's like Dragon Ball Z, right?
Dragon Ball Z, exactly. Or Star Wars with the force push. It's lightning. Lightning is just electrons just spilling out of the clouds. Lightning and a spark is electrons just spilling through the air. It's very difficult to control. So because we want a system that does things quietly and nicely and reproducibly, we run our electrons through conducting pieces of metal called wires. It just makes things a lot easier. There's nothing wrong with playing with lightning and sparks and plasma, but it just makes it difficult. And there are people who do play with those things, specifically inside labs. I don't want to ask your criminal record. Anybody just for fun ever get tasered? You ever seen a taser go? Have you seen the spark? A taser is the same thing.
No, I looked away.
Yeah, a taser just takes raw electrons and just throws it into your body. And what it does is it completely disrupts, as you guys already know, because you probably studied biology in high school. What animates me right now, in addition to my muscles moving, there's also electrical impulses through my nervous system, just like there's wires through that system up there. We also are electron-based. We're not robots, but we're sort of a hybrid between electronics. And when you just fill the nervous system with extra electrons, it completely shorts it out, and it just causes function.
So that's why you pee yourself.
Everything. You lose all body function. You're just down. You can't stand up. It usually knocks you out sometimes. It overloads the circuits in your brain. And yeah, you lose all bodily function. Your muscles just stop. They stop following your commands, and you're down. That's the desire. But the desire is that it's not lethal, that it's only temporary until your body says, what the hell was that? It feels like getting struck by lightning. So what we want to do is we put, on purpose, we connect the negative side of the battery. It's negative because it has all these extra electrons, to the positive side of the battery, because it's missing electrons. We do so through wires, and as you guys already know, because we talked about it before, that's called a circuit, an electrical circuit. So the way to measure the push of this battery is to create a circuit. And what we're going to do is we create a circuit that happens to be through these wires, this black wire and this red wire. Just by convention, the red wire is supposed to be attached to the positive side. This is just by convention. And the black wire on this guy over here, that's not always the case, so don't just walk up to a bomb scare and say, no, stand back, I know which wire to cut. It just depends on what, you can make it any color you want. It's just on this machine, red is positive. And what I can do is I can create a circle or create a circuit. So what I'm going to do is I'm going to place the black wire, I'm going to attach the black wire on the negative terminal and the red wire on the positive terminal that has a dimple. And then inside this circuit is this yellow voltmeter that's inside the circuit. And hopefully it's going to measure the push and tell me how many volts there is. It's difficult to see with your eyes, so we have to measure it with a machine. So I'm going to take the black end and touch the bottom of the battery, and I'm going to take the top end. Any guess how many volts this battery is?
1.5.
1.5? How'd you know that?
Standard.
Because it's damn written on the side. It's a AA battery, and they are standard because otherwise it'd be difficult. 1.586. Crap, that rounds to 1.6. Is it broken? Is it a bad battery? Should I take it back to the store? Hey, I came in to buy a 1.5 volt battery and you sold me a 1.586 battery? Any guess? Let's check it out. So this guy really does have some writing on here. Let me see what it says. Sorry, I'm not a very good hand model, so I apologize. There's the positive side with the dimple up top, and there's the bottom side. Looks like I have a black marker on my finger. Made in USA, Energizer Holdings, St. Louis, Missouri, and it has an EU certification, and it has, looks like, does anybody speak, is that Korean or Japanese? I don't know. Alkaline battery, AA. Oh, there it is. Fantastic. You see what that guy says? Up here, towards the top. It's really small. 1.5 volts. So this is a AA size format, E91, LR5, AM3, 1.5 volts. Okay? And they're standardized because if you build a system that needs a certain amount of push, you don't want extra push or your system will explode. Or you don't want not enough push or your system won't work. This guy happens to have, I'm sorry, we're back again. If I can do it properly. 1.586, okay? This happens to be the 1.5 on the other side. It's not attempting to round. It's saying it's about 1.5 and it's at least 1.5. We'll be studying a little bit later what we can do to make sure that it's not too much higher than 1.5. This appears to be a fresh, normal, ready-to-go battery, okay? Just like when you buy a package of Oreos or you buy a package of Lay's potato chips, if you were to weigh the bag and it weighed much less than what you bought, you'd probably be pissed. But if it weighed a little more than what you bought, you say, hey, I got an extra Oreo, okay? That's how the manufacturers work, okay? The battery is usually a little bit higher than you need, and then the electronic circuits can make sure that that it's not too much. So that's this guy. I've intentionally grabbed another battery that was older. I put a red piece of tape on it. You guys already know why I did it. This is not a fresh battery. It's an older battery. This is a different manufacturer. This is Panasonic. It has the giant plus up there. Okay, has the giant plus up there. Again, same dimple side on the plus. Same negative side down here. It's still supposed to be 1.5. Let's get all dizzy by playing with the zoom over here. Black on the bottom, the top. This guy's 0.912. Okay, he's not a totally dead battery. A totally dead battery would be 0 volts, but he's definitely much less than 1.5. So if I were to stick this into a Wii controller or a fire alarm, it would probably complain to me and say, "Hey, I don't have enough push." This is a battery that has already been used. In fact, I stole this out of a Wii controller that we had downstairs. I think it's been there for a while. So it needs a little. This is a chemical battery. There's a chemical reaction going on to provide the voltage. It's not a rechargeable battery. Anybody ever see or hear or on YouTube what happens when you try to recharge a chemical battery? It explodes. The answer is always it explodes.
You know, I was trying.
Don't put a chemical battery, a non-rechargeable battery, in a rechargeable battery recharger. It will explode.
You know, when I was a kid, I was trying to recharge a battery using a spoon in the fire.
Oh, fantastic! You could use heat.
Yeah.
Did it work? No. It didn't explode.
Burned out my Game
Anybody familiar with this battery? The little square guy. A lot of use in smoke alarms. 9-volt battery. Why would you call it a 9-volt battery? Because damn it, it's a 9-volt battery. Yeah, exactly. Oh, by the way, it's written on the side. This is a 9-volt battery. Okay, so I guess this guy has a different format. Obviously, it does have two ends. This is sort of bent in the middle. So rather than having a negative on the bottom and a positive on the top, which is the format of these cylinder batteries, a 9-volt battery, which is square, has these two guys. So one of these guys is positive, one of these guys is negative. I forget which is which. Let's see if they tell us here. There's a little tiny plus sign on this side, which is the smaller terminal, and then on this side is the negative side. So positive is negative. Let's go ahead and measure it. Let's see what we got. So positive was the smaller guy. That gets the red side. 9.57. This was a new battery I took out of our new battery box. Again, it's a 9-volt battery. It's a fresh 9-volt battery, so it's 9.57. So it's a little bit stronger than 9 volts. Again, the idea of we're going to charge it a little bit higher than we need it. We'll be playing it with this voltmeter in lab. There's our 9.57. If I mistakenly take the leads and I switch them, and I put the black on the red terminal, is it going to explode? What should I do? Are you afraid for my safety up here? What's going to happen if I switch the battery around?
Negative.
It just says it's negative. It just says, idiot, you have it the wrong way. Okay. Remember, for those of you who are with us in physics, positive usually meant if you drew a system like, oh, by the way, here's x, and positive x is this way, and negative x is this way. Positive meant we were heading that way, and negative meant we didn't run that way. That's the same thing here. Positive and negative just means direction. So positive in this sense means from the negative all the way around to the positive, okay? That's the positive direction. And then down here, this is the negative direction. I just have the meter in backwards if we're talking about the direction of the individual electrons. So 9-volt battery. Does anybody else know how to test a 9-volt battery if you don't have a voltmeter? Just you can use your tongue. Are the ones who are done that? Why can't you use your tongue with this guy? Because you can't read both sides unless you have a really, really fantastic tongue. Tongue-wise, you have to touch the top and the bottom. This one's pretty easy. I'm not going to do it because it really does. So what happens when you put a wet, slimy tongue across the positive and the negative? It's like a low-power taser. It tasers your tongue. And you go, And I believe, the last time I've done it, which was, I usually don't like to do it, that is, you get a taste. I think it tastes like acidic, like sour. So obviously the metal itself is not sour, but the electric current, again, tases your taste buds, and whatever sensation you get, your brain says, well, that was odd. I'm guessing it's sour. But you get a little shocked. So, yeah, I'll keep this away for anybody. So, yeah, you can test these batteries by just putting your tongue on it. If nothing happens, then it's just like licking a piece of aluminum, like a spoon. Nothing's happening because there's no battery in it, okay? It's just a regular system. We're going to put this cover back on. Anybody familiar with a car battery? Anybody know what the voltage is of a car battery? They're pretty big, right? They're big batteries for your car. They're like this. They're huge. Again, 2 terminals at 9 volt. They're 12-volt batteries. But again, it's not a lot of voltage. You would say, why in the world would? It's not a lot of push. It turns out that there's a lot more current, but it's just a 12-volt battery in your car. It's not much. Okay?
So if you were to put your tongue in it, would you die?
Probably yes. Yes.
To be clear.
I don't think you die.
I think you would eat.
You really burn your tongue off. I have not tried this on purpose, but I've done it accidentally. I'm still alive. If you happen to be using a metal wrench and you're like working on your car and you accidentally rest the metal wrench from here and here, it will spark like crazy. Hopefully it won't, again, my stories always end with explode. Hopefully it won't explode the battery. I've heard stories on YouTube where that happens and they've welded the wrench to the battery. You can't pick it up anymore because it just melted. It melted the wrench. So yeah, I would suggest that you try to,
I'll take your advice.
don't put your tongue on a car battery. They're pretty huge. Again, you don't need much push to get things to happen here. So let me take these batteries out of our little motor that we had. Notice these batteries are not the same size. One of the other things that this meter can do is it can measure not the push of a battery, but it can measure the resistance of, quote unquote, a straw. And I did walk with this guy over here. Okay, need a little space. We said a straw will take air and move it from there to there. So a wire almost looks the same. It has like a plastic coating, and then there's the wire in the middle. They're very similar in how they look design-wise. One's hollow for air, one's filled with a wire, and the electrons do exactly that. They flow through to the other side. However, as we saw before, just adding the straw to the balloon slowed it down a little bit. I think it was 2 seconds for just this guy, and then it was maybe 4 seconds with the straw. I think it was 6 seconds with the straw. It made it larger. Just adding the straw slowed things down because the straw has resistance. Same thing with this wire. Just adding this wire to that battery will increase the resistance and cause the flow of electrons to be slower than if we were to just short circuit it. So one of the things we need to do is we need to measure what is the resistance of this wire, just like what is the resistance of this guy. So what I'm going to do is over here, I'm going to change this multimeter. It says multimeter. I'm going to move it over to resistance mode. You'll notice this thing does several things. That's selected here. This guy is measuring ohms. We mentioned that Frederick Ohm is the guy who sort of invented all of this. So we talk about resistance here. So volts-wise, 1.5 volts, a 9-volt battery, a 12-volt battery for your car. You know, a handful of volts is usually what we work with. Resistance-wise, the resistance can be very, very low. So what I'm going to do is I'm going to take this wire and sort of make a nice little hook on it. And now we're in mode over here. It turns out with this machine, I can go ahead and measure the resistance. I'm going to make a circuit out of this. This wire. I'm going to see how much resistance there is. How difficult is it to push the electrons through here? So as I do this, about 0.2. Okay, so there's not much 0.1, 0.2. I'm just touching this wire. It's kind of just a regular old wire. It's almost even saying 0 sometimes. It's just me not doing a very good job of it. There we go. About 0.2, 0.1. It's a fractional amount of resistance, so we would need a 10 times longer wire to even get to 1 ohm. Okay, so ohms are usually low when we're talking about just pure metal or pure wires. We usually don't worry about the resistance of a wire because it's usually 0.1 or even below 0.1. I've brought along this little slug. It's a little piece of aluminum. Aluminum is, this guy over here is nickel and copper. Nickel copper is very conductive. Aluminum is about 2/3 as conductive. It's about 60% conductivity. But I can do the same experiment by touching these guys over here. So this guy, about 0.2, about 0.1. So on the order, about the same thing as that wire, but you'll notice it's much shorter. Okay, again, I mentioned that the aluminum is not as conductive as this guy is. So this also is about 0.1 ohms. So we would say this is a very good conductor because its resistance is very, very low. If we go over here to a real straw, I'll just take this real straw here. It's made out of polymer or plastic. plastic is often a very poor conductor. So if I take this straw, which is not metal, and I put it on here, and I measure the resistance, if I can get it on there. Maybe you can do it. Okay. Notice I'm not getting any measurement at all. We're in units of mega ohms, millions of ohms. This just means overload or over limit. It just means it's so high you can't see it. So that straw is not a very good conductor at all. It's a very poor conductor. But what we can do is we can take these batteries. Notice I still have a battery in there, and we saw this guy run on Wednesday. If I turn the switch, I expect it to turn on, and nothing's happening. The reason it's not happening is this system needs to be a circuit, and it's designed to have 4 batteries connecting the top and the bottom. So what we have now is we have a system where we've broken the connection. So this guy's not running at all, but I can reconnect it, make sure the battery is turned up, by putting these conductive, the reason why they're made this size is they are the same size as a battery. They're meant to be conductors, but obviously these are just conductors. They have no battery aspect. There's no voltage. I didn't test that, right? Maybe I should test that. Let's go back to volts, and let's test the voltage of this little piece of aluminum. Oh, it's negative, I guess. It's 0. It's not a battery. It's just a piece of aluminum. If I go ahead and put this thing on, if it had a battery, that'd be cool. So now I believe I've created a circuit. I think I'm connecting all the electrons to the system. So if I turn this thing on, well, that's gentle. That's nice. Remember how crazy loud this was on Wednesday? Why? I'm sorry? More power. We had more push. We were pushing with 4 batteries before. Now we're only pushing with 1 battery. Okay. What this design does is, remember that the dimple is positive and the negative is down at the bottom. If we stack these things, this is 1.5 volts. This is 1.5 volts. Now I have 3 volts of push. And if I go ahead and put this guy on top of it, now I have 4.5 volts of push. And if I put all 4 of them, then I have 6 volts of push, right? 3 and 3. So if you go into an electronic device, I think the Wii balance board very famously takes 4 of these guys. So it runs off of 6 volts in the bottom. It needs more push. So if I remove, let's just take a look at this guy. Here's gentle. That's the push from 1.5 volts. If I take out one of these slugs and I put in another battery, I think this is twice as much push. That sounds about right. And then, of course, we could go ahead and go back to where we were before. I think this is even twice as much as that. I have to make sure they're in the right direction so that they're all facing the right direction. Why did it go down? Maybe I have a battery in backwards. I would have thought it would have gone higher. It sounds like it's going slower. Maybe the batteries suck. Maybe I put in bad batteries. I'm not sure what they are. I should have done this demonstration before. Anyway. Explosion! Sorry, just back again. If these were all fresh batteries, the thought would be that they would keep on getting higher and higher and higher because I'm adding more and more push. Okay? So we can increase the push by adding more volts. One way to increase volts is to add more batteries. Electronically, we don't do that because it's very inconvenient. We have a volume knob, and you just go ahead and turn the knob and it increases the push. And we'll be seeing that in a little bit how that actually works. Okay. So here is again, here's a very short wire. That's not a battery, that's a wire. It's a very thick wire. And I measure volts because I'm an idiot. There we go. So very, very low. 0.2 this time around, 0.1. In real electronics, we don't want to have these big, bulky pieces of metal. Makes things heavy. We like to have them small. So what we can do is we can take the
material that this straw is made of that has amazingly high resistance, and we can take the material that this aluminum was made out of, which has very, very low resistance, and of course we can melt them together. Not physically melt them, but we can construct a new piece of thing that happens to have some resistance in between. And that's what this guy is. Okay. He's really, really tiny. You'll notice he happens to have, I say he, here's a wire. There's our wire. The thickness of the wire is about the same as the thickness of this wire. Let me go ahead and run this guy down here. This guy happens to have a very thin wire, and then it happens to have this little device. Let me get rid of the let me get this guy out of the way so it stops auto-focusing on that, and have it auto-focus on this. There it is. So this is a real resistor. My shoe is untied. I'm going to trip, and then I will explode. So there's a little resistor. What makes the resistance high on that is not its size. Obviously, it's very tiny. What makes the resistance high is what it's made out of. It literally is made out of material that is an insulator, doesn't conduct very well, and a conductor. So we can measure what this resistance is. So let me go back to this guy, get our machine back here, and we're measuring resistance, and I want to measure resistance. What I'm going to do is I'm going to bend some hooks on the end here so we can see what they are. I'm going to measure the resistance. Okay, 1.979 units kiloohms. So this is almost 2,000 ohms. Remember, our wire before was only 0.1. That piece of aluminum was only about 0.1. This is, well gosh, 0.1 to 2,000 is 20,000 times more resistance. That's a lot of resistance. So kiloohms is about the region of resistors that we're going to be working with this semester. We're working with thousands of ohms and maybe even millions of ohms, because when you work with only 0.1 ohms or 0.2 ohms, you're really talking about a wire and not much things change. So one of the systems we need to work with is, I could walk around with this meter all day and figure out what that guy is, or I can just read off of the device what size it is. Okay, this is really tiny. You can see how it's really tiny. It's like the size of an ant, like a carpenter ant. It's really tiny. It's really hard to see. Even my old eyes can't see it. So hopefully you can see on the back that it has some colored bands around it. So it's a system. It is a conceptual system, and it is a system that takes input of information. I need another guy over here. So the resistor itself provides resistance, but there's a system that takes information on the way in and information on the way out, and process-wise is really 4 little bands or 4 little lines or 4 little stripes. This piece of paper, we're going to be referring to both of them. We're going to use, I put the fantastic ISBT logo up on the front. We're going to be looking at the back of this sheet first, so if you would, take a look at this guy. We're going to see if we can find out what that value is. It'd be convenient if we could read what that resistance is without having to run around with a multimeter running around. Thank you. The difficulty is that this little device is so small, even if we wrote it in English, 1.9 or 2,000 ohms, 2 kiloohms, we need a magnifying glass to see it. So there's a system, and the system is not difficult at all. The system is explained by this chart down here. If I grab this guy, what we're going to do is we're going to start with the same color as the color of my marker, black. And then we're going to move over and we're going to go to something that's not as black, but still kind of muddy, and that's brown. So black will be first, brown is next. I didn't invent this. The people who were at the engineers invented this system. Then we're going to go through the colors of the rainbow in order. Everybody know the colors of the rainbow in order?
Yeah, Roy G. Biv.
Roy G. Biv, fantastic. The only thing that's not, it really is Roy G. Biv, but we're not going to use I. What the hell is indigo? Indigo is a fantastic color. It was probably my favorite crayon as a kid. Hell, it was my favorite crayon yesterday. We're not going to use indigo, okay? So we're going to use Roy G. Biv, okay? No I. Violet, yeah, we like violet, but indigo and violet are so close to the I, they said, we're not using indigo, okay? So, Roy G. Biv, okay? It's Roy G. Biv without the I. And then we're going to go to metallic colors. I forget the order. Gold, silver, and none. Gold and silver, and then no. Get these guys out of the way.
How about gray and white?
And then, oh, that Miss Gray and White, it's gold silver at the end. I'm sorry, this guy.
Yeah.
Gray, thank you. White, then gold and silver. Thank you for reminding me because I would have messed up. Fantastic. So, black, brown, as a purist, I think this would be really dark gray. But black and brown, Roy G. Biv, and then gray, light gray, and then white. That's the spectrum of colors. And then we go to metallic colors, gold and silver. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? That gives us 10 digits. And when you count to 10, on 10 digits, your fingers, you can start with 1 and then say this is 10. But what we want to do is we only want to use one digit at a time. So we're going to use this. That's 10, 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a system. We'll be talking about gold and silver in a little bit. Almost finished. We're just going to finish this up now. We'll complete it on Monday. These stripes, there's 3 stripes that are sort of usually together, and there's 1 stripe that's usually separated by itself. What does that mean? I can't really tell. These guys are exactly the same. This guy will be a metallic stripe, or it won't be at all. So this is either gold, silver, or blank. So it's these 3 guys that we're worried about. So this guy is red and black, followed by a red. Okay. So this is a red stripe, followed by a black stripe, followed by a red stripe. It's a system. It's not a secret code. It's a very well-known code. This is the way this works. 1 number, second number, times 10 to the number. That's the pattern. It's not specifically scientific notation. Remember, scientific notation only ever had 1 number and then a decimal place. This has 2 numbers, a decimal place, and then times 10 to the so-and-so. I didn't invent it, someone else did. I'm guessing that this system and the scientific notation were probably invented at the same time. Red is a 2. Black is a 0. Red is a 2. Still a 2. 2, 0 times 10 to the 2. 2, 0 times 10 to the 2. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is
10 to the what?
10 to the 2 is 100.
It's 100.
it's 100.
Yeah, because you have to times it by each number, so it's 100.
Fantastic. 20 times 100. Oh, this math.
Oh, that's easy. It's 2,000.
2,000. What did we measure our resistor to be? 1,981, right? That's kilo ohms, so 1.2. So it's not exactly 2,000. They can't manufacture it exactly, so they include this gold band. And if you look on our chart here, gold means plus or minus 5%. So it's 2,000 plus or minus 5%. That's our guy. Working with electronics does not mean your entire day is spent reading these stupid little bands, okay? I just wanted to show you that's why they're there, okay? It's another system we needed to solve a problem. Fantastic. End of week 2. Have a fantastic weekend. Watch out for any precipitation. I'll see you on
Yes, it's like on your mouth. As